This tape is for synthesists and other musicians who desire to know more about sound as it relates to music. In particular, it will teach you how synthesizers can be used to produce sonic imagery. In upcoming lessons on this tape and Volume 2, we will explore and explain virtually all aspects of analog and digital synthesis. Specifically, Secrets of Analog and Digital Synthesis will provide you with a set of meaningful tools and knowledge which can be applied to virtually any electronic musical instrument. In this first lesson, we will concentrate on how sounds are generated and perceived in the physical world. This is of vital importance to synthesists, since we must both imitate and innovate sound events. There is more to the art of sound design than tweaking parameters of a favorite preset or twisting knobs into some bold new configuration. A good synthesist has much in common with a good magician or a good impersonator. He must use sleight of hand and misdirection. He can imply conditions of musical and acoustical context and thus strengthen his sound imagery. If we could name and understand all of the various aspects of sound, how would it be useful to our real-world experience as musicians? The foundation of the sound designer's toolkit and bag of tricks is a solid understanding of the physical nature of sound and our perception of it. Listen to the sounds coming from your VCR right now. You are undoubtedly making associations with specific instruments and musical situations. You are also visualizing specific physical factors about the environments in which these sounds occur. In your mind's eye, you may be forming concrete or abstract images, but you are getting definite impressions about the reality in which these sounds were made. Yet what you are hearing has no basis in the real world. These sounds were, of course, generated electronically. And while this may not sound exactly like a Stratocaster feeding back, you probably thought of some related image before you thought of hands on a synthesizer keyboard. The point is, your mind will subconsciously order sonic information into imagery. This provides the sound designer a subtle yet effective manner to reinforce sonic illusion. Sound contains a set of components or parameters. We perceive changes in these parameters as clues that help us evaluate and identify what we hear. We will learn how to use synthesizers to control and simulate these clues. We will see how to break sound down into its basic parameters so that we may eventually synthesize sounds that exploit to our fullest advantage any of the clues we choose. Okay, where do we start? Where exactly does sound originate from? Or more to the point, what makes a sound musically useful? All sounds have three main parameters. We'll call them the big three: pitch, loudness, and timbre or tone color. What is the highest or lowest pitch you can hear? The loudest and softest sounds. Why does the same note played on two different instruments sound different? Let's look at two sources of sound, one acoustic and one electronic. Plucking a string on this viola or playing a key on the synthesizer will create sounds. The viola creates sounds directly. The synthesizer itself makes no sound. Its signals must be converted by a speaker into vibrations before it can be heard. Remember, synthesizers make no sounds by themselves until they are connected to a speaker. By watching and listening to these two sources of sound, we can observe the following. Something is moving when we hear a sound, and that motion is too fast for us to see clearly. As the sound fades away, the motion lessens. If I stop the motion, the sound stops. From these observations, we can make the following deductions. The generation of sound seems to be linked to motion, specifically vibration. Since sound has three main parameters, pitch, timbre, and loudness, it should be possible to find specific aspects of motion that relate directly to the big three. What exactly is sound, and how does it travel from its source to our ears? Sound is a form of energy. It is transmitted in waves. The motion of a vibrating object, like a tuning fork, disturbs the air around it. This disturbance moves outwards from the source in all directions. This traveling disturbance is similar to the waves formed on the surface of a still pond when you drop in a stone. Sound waves are actually minute changes in air pressure. They are virtually invisible, but we do have a device that will allow us to see sound waves. It is called an oscilloscope. We will be looking at the scope quite often in this course. Here are the basic rules for interpreting the images that it produces. When the oscilloscope is used to display sound waves, it is showing us changes in air pressure that occur over a period of time. Vertical distance on the scope represents measurements of air pressure. The center line represents normal air pressure. Distance above the center line represents higher than normal pressure. Distance below it represents lower than normal pressure. The horizontal distance from the left edge to the right edge represents a fixed amount of time. This time scale can be varied, and for sound measurements it's typically quite short, hundredths or thousandths of a second. Here is a typical scope image. This kind of repeating curve is called a wave. We can name the various parts of a wave, and in doing so we will have names for the various parameters of the vibrating string or loudspeaker's motion. Let's look at shape first. Not all repeating curves look just like this one, so the general term used for the shape of a wave is, simply enough, wave shape or waveform. Often a wave is referred to by the geometry of its wave shape. This wave is called a sine wave. Some other geometric waves are sawtooth and square waves. Geometric waves are quite common in synthesis, for reasons we'll soon find out, but not all waves are geometric. The highest and lowest parts of the wave are called peaks. The vertical distance between peaks is called amplitude. The horizontal distance from any given point on a wave to a point one full swing away is the wavelength. If the wavelength is expressed as a measure of time, it is called a period or cycle. Often, wavelength is expressed as how many periods or cycles occur within a fixed amount of time. This is called frequency. The more cycles you see on the scope, the higher the frequency. When measuring sound waves, frequency is often expressed in units called hertz, which stands for cycles per second. The abbreviation Hz is often used for hertz, and kHz for kilohertz, or thousands of cycles per second. Now we can equate the parameters of a wave with aspects of the viola string or loudspeaker's motion. Amplitude is the equivalent to the distance that the string or speaker moves back and forth when vibrating. Frequency is how quickly a vibrating object moves, and waveform is the overall pattern or shape of the vibrating motion. Remember the big three, pitch, timbre, and loudness? Do you think they could be related in any way to frequency, wave shape, and amplitude? You bet they are. This is a roll in Juno 106, and this is what it sounds like. Watch the waveform and see what happens when I change the volume of a note. Can you see that it is the wave's amplitude or overall height that is changing? Its shape and frequency remain constant. A sound wave, like all moving waves, is a form of energy. The amplitude of a wave is an indicator of how much power that wave contains at a given moment. The power represented by a sound wave's amplitude is usually referred to as intensity. It is the parameter of sound that we sense as loudness. In your manual is a detailed explanation of the relationships between intensity, loudness, and perception. Here is a summary of the important facts. There are definite limits to the softest and loudest sounds we can perceive. The softest sounds we can hear occur at the threshold of sensation. We'll call this ultra pianissimo. The loudest sounds occur at the threshold of feeling, which we'll call mega forte. The softest sound could be doubled in apparent loudness only 13 times before it reached the upper limit of loudness. Our ability to discern discrete changes in loudness is not very refined. If the loudness scale from ultra pianissimo to mega forte were split into 130 steps of equal volume changes, we would not be able to hear the individual change in loudness between any two adjacent steps. There are many ways to change pitch on a synthesizer. I'll use the bender, and again, watch the waveform. You can see that the number of cycles of the wave increases as the pitch is raised. The amplitude and shape remain constant. Our perception of pitch is related to frequency. As we have seen, frequency is a measurement of time, how long it takes for an event to repeat. The frequency of the Earth's rotation around its axis is once per day. The frequency of a minute hand traveling around the face of a clock is once per hour. The frequency of quarter notes in a Sousa march is 120 per minute. Rhythms are low frequencies. We hear them as a series of events. As frequency is increased, these events become closer and closer rhythmically, until at some point they begin to blur. There is, in fact, a kind of twilight zone, where some people hear frequency as rhythm and others hear it as pitch. We are very fortunate to have with us today Mr. Frank Marilla, who has graciously taken time from his busy schedule as a star of a cult classic television show. Mr. Marilla has agreed to help us explain this nether region of pitch and rhythm. The heartbeat of an individual in good shape, like Frank here, is about 60 cycles per minute, or 1 per second. When we listen to this heartbeat, thank you, Frank, we hear its frequency as a steady rhythm. By connecting Frank to this device, we can safely raise his heartbeat. Remember, this is a carefully controlled experiment. Don't try this at home. The rhythm becomes faster and faster. You okay, Frank? As the frequency is increased further, we will begin to hear a pitch. I hear pitch right about here. That looks invigorating, Frank. This is a frequency of about 20 hertz, and we call this the lower threshold of pitch. As we continue to raise the frequency, hang in there, Frank, this is why you get the big bucks. We will eventually cease hearing pitch. If you have a dog, it's probably barking now. We call this point the upper threshold of pitch. When we were young, this could have been as high as about 20,000 cycles per second. But after years of rock and roll and industrial noise and MTV, this point begins to drop. Most of us still hear pitches up to around 16,000 times per second. Let's bring Frank back down to normal so he can relax. Thank you, Frank. You were great, babe. The total range of pitches from the highest to the lowest that we can hear is about 10 octaves. The octave is the most common pitch measurement used by musicians. It represents a net frequency change by a factor of 2. In other words, multiplying a frequency by 2 will cause a pitch to go up 1 octave, while dividing it by 2 will cause the pitch to go down 1 octave. The lower threshold of pitch, 20 Hz, could be doubled only 10 times before it reached the upper threshold of pitch. This means that there is a definite limit to the highest and lowest pitches that we can hear. We are much more sensitive to changes in pitch than we are to changes in loudness. We can all easily hear changes in pitch of a semitone. That is the equivalent to 1/120th of the total pitch range. Most musicians can discriminate between two pitches that are only fractions of a semitone apart. Watch how the waveform changes as I change timbre. As you can see, changing the sound's timbre alters the wave shape. The frequency and amplitude remain constant. To a sound designer, timbre is probably the most important parameter of sound. In order to get a better look at the causes of timbre, we will look at sounds in a new way. This is a spectrum plot. We will be using them quite often in demonstrations that relate to timbre. Once again, the fine details are explained in your manual, but here are the basic points to keep in mind. A spectrum diagram shows a waveform not as a single shape, but as a collection of vibrations called partials. The frequency and amplitude of the various partials that make up a wave determine its overall shape and therefore timbre. Each vertical bar in a spectrum represents one partial. There is a natural order of frequencies that occur in nature called the harmonic series. Most musical sounds are made up of partials whose frequencies are a subset of this series. The lowest frequency in the series is called the fundamental, and it is the frequency we perceive as a sound's pitch. Since timbre is independent of pitch, it is not the actual frequencies that are important in a spectrum plot, but the intervals between the fundamental and other partials. For this reason, the intervals are expressed as ratios, simple whole numbers, 2, 3, 4, 5, and so on, times the fundamental's frequency. It is wave shape that allows us to recognize a friend's voice from among the voices in a crowd, or hear the difference between the same A flat played on two different instruments. A wave spectrum is like a fingerprint. No two wave shapes have exactly the same spectrum. A sawtooth spectrum looks like this. It has partials at all of the harmonic frequencies. A square wave spectrum contains partials at only the odd harmonic frequencies. A triangle wave spectrum is similar to a square wave's, only odd harmonic frequencies, but their individual amplitudes are much less than a square wave's. This is why a triangle sounds duller than a square wave. Wave shapes that are not geometric have partials that are not all at harmonic frequencies. Most musical sounds have timbres that change over the course of a note. If we could freeze the timbre of a brass note, we would see a spectrum like the one shown here. A clarinet has a spectrum very similar to this, and a metal bell might have a spectrum like this one. Remember, a spectrum plot is just another way of looking at wave shape. As we will see in upcoming lessons, it is a synthesizer's wave shaping abilities that make it such a capable imitator and innovator of sounds. Okay, let's review. What we perceive as sound are waves that originate at a vibrating source and are transmitted through the air. The three parameters of sound, pitch, timbre, and loudness, correspond to the three physical aspects of a wave's motion: frequency, wave shape, and amplitude. The sensation of pitch is directly related to a sound wave's frequency. There are definite limits to our perception of pitch. We can hear very minute changes in pitch. Frequencies below 20 Hz we perceive as rhythms. The sensation of loudness is directly related to a wave's amplitude. There are also limits to the loudest and softest sounds we can perceive. We can hear loudness levels between the softest whisper and the roar of a jet engine, but our ability to discriminate between small changes in loudness is not very refined. The sensation of timbre is directly related to a wave's shape. Different wave shapes are made up of many individual vibrations that occur simultaneously. These vibrations are called partials. There is a common structure of partials called the harmonic series. There is no limit to timbre perception. Any sound wave with a repeating shape will be heard as having a specific tone color. We are extremely sensitive to changes in timbre. In fact, your ability to understand what I'm saying right now is almost wholly dependent on your ability to hear changes in timbre. The big three, pitch, timbre, and loudness, can be changed independently of each other.